Hello everybody, this is Mika Seppälä. The ratio and the root tests are important tests that allow us to figure out whether complicated series converge or not. In this video I discuss these two tests. Consider the series summation k from 1 to the infinity ak. Assume that the quantity absolute value of ak plus 1 divided by the absolute value of ak has the limit q as k goes to the infinity. If this limit is less than 1, then we can conclude that the series summation k from 1 to the infinity ak converges. If the limit q is greater than 1, the series diverges, and the test is inconclusive if this limit is 1. This is the ratio test. Consider the series summation k from 1 to the infinity k squared divided by 2 to the power k. To decide whether this series converges or not is not easy using the comparison test or the integral test. Those could be applied, but they would lead to long computations. We may use the ratio test instead. In the ratio test, we have to study the quantity ak plus 1 divided by ak and the absolute value of that. In this case, ak equals k squared divided by 2 to the power k. So the absolute value of ak plus 1 divided by the absolute value of ak is k plus 1 squared divided by 2 to the power k plus 1, and this ratio divided by the ratio k squared divided by 2 to the power k. This simplifies to 1/2 times k plus 1 squared divided by k squared. But k plus 1 squared divided by k squared approaches 1 as k goes to the infinity, and therefore this whole quantity approaches 1/2 as k goes to the infinity. And therefore we may conclude by the ratio test that this series summation k from 1 to the infinity k squared divided by 2 to the power k converges because the quantity of the ratio test, that is the limit as k goes to the infinity of absolute value of ak plus 1 divided by the absolute value of ak is 1/2, and that is less than 1. The series summation k from 1 to the infinity 1 divided by k factorial is an important one. Now, to study the convergence of that can be easily done using the ratio test. In this case, ak is 1 over k factorial. K factorial here means the product of all numbers 1, 2, 3 all the way up to k. So ak plus 1 absolute value divided by ak absolute value is 1 divided by k plus 1 factorial, and that divided by the ratio 1 divided by k factorial. This simplifies to k factorial divided by k plus 1 factorial. K factorial is the product of numbers from 1 to k. K plus 1 factorial is the product of numbers from 1 to k plus 1. Therefore, this simplifies to 1 divided by k plus 1, and that approaches to 0 as k goes to the infinity. Therefore, we conclude that this series converges because the limit as k goes to the infinity of the absolute value of ak plus 1 divided by the absolute value of ak is 0, and 0 is less than 1. Let us take a look at what the ratio test says about the harmonic series summation k from 1 to the infinity 1 over k. In this case, ak is 1 over k. All ak's are positive, therefore also the absolute value of ak is just 1 over k. Now, for this series, the absolute value of ak plus 1 divided by the absolute value of ak is therefore 1 over k plus 1, and that ratio divided by 1 over k. This simplifies to k divided by k plus 1, and this has the limit 1 as k goes to the infinity. Therefore, we conclude that the quantity of the ratio test, that is the limit of the absolute value of ak plus 1 divided by the absolute value of ak as k goes to the infinity for the harmonic series is 1. and the harmonic series diverges. Let us use the ratio test to study the series summation k from 1 to the infinity negative 1 to the power k plus 1 divided by k. This series is the alternating harmonic series which converges by the alternating series test. Let us see what the ratio test tells us about this series. For this series we have that the absolute value of ak plus 1 divided by the absolute value of ak is 1 divided by k plus 1 and that divided by 1 divided by k. And this simplifies to k divided by k plus 1, which approaches 1 as k goes to the infinity. Hence, the alternating harmonic series is a series which converges and for which the ratio test quantity equals 1. The harmonic series, on the other hand, diverges, and also for that series the ratio test quantity equals 1. Therefore, we conclude that if the ratio test quantity equals 1, the test is inconclusive. The ratio test tells us that if the quantity limit as k goes to the infinity, absolute value of ak plus 1 divided by the absolute value of ak is less than 1, then the series summation k from 1 to the infinity ak converges, and that if this quantity is greater than 1, the series diverges. And we have now seen by examples that the test is inconclusive if this quantity q equals 1. Let us prove that part of the ratio test which says that if the limit as k goes to the infinity of the absolute value of ak plus 1 divided by the absolute value of ak is less than 1, then the series summation k from 1 to the infinity ak converges. Denote this limit by q. Now if q is less than 1, then we may of course choose a number p between q and 1. And since the limit of the absolute value of ak plus 1 divided by the absolute value of ak equals q as k goes to the infinity, these quantities, the absolute value of ak plus 1 divided by the absolute value of ak, become arbitrarily close to q. In particular, there is a number kp such that whenever k is greater than or equal to kp, then the absolute value of ak plus 1 divided by the absolute value of ak is less than p, because p is greater than q. This follows immediately from the definition of the limits. This means that the absolute value of ak plus 1 is less than p times the absolute value of ak for k greater than or equal to kp. This means inductively that the absolute value of a kp plus n for any positive integer n is less than p to the power n times the absolute value of a kp. This is the crucial observation. Consider now the series summation n from 1 to the infinity p to the power n times the absolute value of akp. Here the summation index is n, and the quantity, the absolute value of akp, does not depend on that. Therefore, this series is a geometric series whose ratio of two subsequent terms is p, and we had assumed that this p is less than 1. Therefore, this series summation n from 1 to the infinity p to the power n times the absolute value of akp is a convergent geometric series. We have seen that the absolute value of akp plus n is less than p to the power n times the absolute value of akp for all n positive. This means that the series summation n from kp plus 1 to the infinity an converges absolutely by the comparison test. And since this converges absolutely, it also converges. So we conclude that the series summation n from kp plus 1 to the infinity an converges. And if this converges, then also the sum where we start the summation from the index value n equals 1 converges as well. And we have shown that the series summation n from 1 to the infinity an therefore converges, proving that part of the ratio test which says that if the ratio test quantity is less than 1, then the series in question converges. Statement of the ratio test is now: suppose that the quantity q, which equals limit as k goes to the infinity, the absolute value of k plus 1 divided by the absolute value of ak, is less than 1. Then the series summation k from 1 to the infinity ak converges. If this quantity is greater than 1, this series diverges, and the test is inconclusive if this quantity q equals 1. In the root test, we study the series summation k from 1 to the infinity ak. Assume that the limit of the quantities kth root of the absolute value of ak exists as k goes to the infinity. If this limit is less than 1, then the series summation k from 1 to the infinity ak converges. If that limit is greater than 1, the series diverges, and the test again is inconclusive if this limit equals 1. As an example of the use of the root test, consider the series summation k from 1 to the infinity, 2 times k plus 3 divided by 4 times k plus 5, and that ratio to the power k. This series is somewhat complicated and cannot be easily studied by the integral or by the comparison tests. Here, the root test shows us quickly that this series converges, because in this case, kth root of the absolute value of ak is kth root of 2 times k plus 3 divided by 4 times k plus 5, and that raised to the power k. So kth root of a quantity to the power k is just that quantity itself. Therefore, this is 2 times k plus 3 divided by 4 times k plus 5, which equals 2 plus 3 divided by k, and that sum divided by 4 plus 5 divided by k. And as k goes to the infinity, this approaches the value 1/2. Because 1/2 is less than 1, this series summation k from 1 to the infinity, 2 times k plus 3 divided by 4 times k plus 5, and that ratio raised to the power k converges. To study the convergence or divergence of a series summation k from 1 to the infinity ak, we have introduced the ratio test and the root test. In the ratio test, we consider the quantity limit as k goes to the infinity of the absolute value of ak plus 1 divided by the absolute value of ak. We call this limit q. In the root test, the quantity is the limit as k goes to the infinity, kth root of the absolute value of ak, and this is called r. The series summation k from 1 to the infinity ak converges if q is less than 1 or if r is less than 1. The series diverges if q is greater than 1 or if r is greater than 1, and the tests are inconclusive if q equals 1 or if r equals 1. These are the ratio and the root tests.